This is your weekly dose of 3-Eye Atlas featuring color change from red dust to green glow, brought to you by the Sleepy Science 100 channel. Before we begin our journey into the quiet cosmos, if you enjoy exploring the deep science of sleep and space, please consider subscribing. Liking the video helps us know that these cosmic journeys are helpful. If you're listening before you fully drift off, we invite you to comment with one word describing how you hope to feel in the morning, such as rested or calm. Now let us settle in. Tonight we will drift through the surprising shift from a reddish, dust-dominated coma to an emerging greenish gas glow. The chemical transformation revealing diatomic carbon emissions as the comet heats. The interstellar visitor's evolving colours painting a portrait of hidden volatiles awakening. Thank you for joining us tonight as we drift far, far out to explore 3-Eye Atlas, colour change from red dust to green glow. Close your eyes now, let yourself sink deeper. And imagine we're travelling backward through time to early July of 2025, when telescopes first turned their patient glass eyes toward this traveller, this visitor from beyond. In those earliest observations, the coma glowed with a distinctly reddish tone, earthy, warm, the colour of ancient dust awakening from reddish slumber. This red was not the fierce scarlet of warning, but something softer, like distant clay illuminated, like rust remembering iron. The cause of this hue, so peaceful to consider, lay in the nature of reflected sunlight dancing across large dust grains suspended in the coma, grains several micrometers in radius, each one a tiny world scattering light, bending wavelengths, favouring the longer reds over shorter blues. The reddish appearance, so similar, we might whisper, to certain D-type asteroids drifting in twilight orbits, and to those curious substances called tholins, complex organic molecules, formed not in moments, but across billions of years through the patient touch of cosmic rays, processing, transforming, layer by slow layer. Tholins, even the word sounds sleepy, ancient. These molecules absorbed the blue wavelengths hungrily, leaving behind that characteristic ruddy tone, the warm embrace of red and orange light, making the early coma appear as if wrapped in a dust veil of primordial organics, lifting slowly to reveal what lies beneath. In these initial weeks, the coma appeared dust-rich, almost drowsy with particles, and minimal gas emission was visible. The comet held its breath, waiting as it journeyed inward. Solar heating had not yet penetrated deeply. The surface, devolatilized perhaps over eons of interstellar wandering, kept its secrets close. But transformation through solar warmth's touch was coming, inevitable as dawn, as the comet traced its path through the inner solar system, approaching perihelion, that closest point to our Sun, scheduled for October 2025, as August gave way to September, and September whispered into October. Activity intensified, subtly at first, then with growing urgency. Solar radiation, patient and persistent, caused increased sublimation of buried volatiles, ices hidden beneath that protective crust, water ice, carbon dioxide, carbon monoxide, all beginning their slow dance from solid to gas, escaping into the vacuum, carrying with them tiny dust particles, expanding the coma. The dust ejection rates, measured carefully by astronomers who never sleep were estimated at tens of kilograms per second in those early phases. Imagine tens of kilograms, every single second. A river of particles flowing outward into space. Then came the post-perihelion observations, November, December of 2025, when careful eyes noticed something unexpected, something beautiful in its quiet way, a faint greenish glow, emerging like buried greens in quiet fluorescence. The coma had shifted, transformed. Colour-filtered images from the Gemini North Telescope, high on Mauna Kea, revealed this greenish hue dominating where red once ruled. The green glow, scientists understood, came from fluorescence of diatomic carbon molecules, C2, two carbon atoms bound together, dancing in molecular embrace. These diatomic carbon molecules, when excited by solar ultraviolet radiation, emit green light, a specific wavelength, a signature. It is the same green we see in many solar system comets. The famous emerald coma of Hale-Bopp comes to mind, but here, in this interstellar visitor, the emergence felt surprising, unexpected, because earlier observations had shown depletion of carbon chains, making this green shift a puzzle wrapped in celestial jade breath. The C2 production increases, you see, as deeper carbon-bearing ices become exposed, as the heating gradient reveals layered chemistry, peeling back like ancient pages of a cosmic book. Let your breathing slow now. Feel the rhythm of sublimation, solid becoming gas, red organics yielding to diatomic whispers. The coma transitioned, not suddenly, but gradually, from dust-scattered red dominance to gas-emitted green ascendance. Multi-filter observations using blue filters, green filters, red, orange, highlighted this transformation, painted in wavelengths, each filter a different window, showing the dust component persisting in red, the gas glowing in green and blue. The composite RGB images revealing an overall greener tint as November deepened into December. Cyanide radicals too, CN, contributed their voice, bluish-green emissions, the CN violet system adding tones to the overall palette. These molecular fragments, produced through photodissociation, parent molecules breaking apart under solar ultraviolet assault, releasing daughter molecules, each with their own spectral signature, their own colour. Spectral analysis confirmed the C2 emission lines, those characteristic swan bands emitting strongly in green wavelengths, while VLT observations detected rising cyanide production, a cyanide surge that correlated with the colour intensification, quiet alchemy of light and gas. The pre-perihelion coma, observers noted, elongated westward, a dust tail prominent, stretching away from the sun like a banner. But the post-perihelion coma took on a more spherical appearance, gas-rich, rounder, softer. The morphological evolution accompanied the colour shift. Form and hue intertwined. Brightness increased too, the comet growing more active, more alive in a sense, though of course it was never living, merely awakening, chemical layers peeling to release their stored energy, their hidden light. On November 26, 2025, the Gemini North GMOS instrument captured particularly striking images of the greenish coma, and NSF Noir Lab released colour composites, showing this transformation from cosmic rust to living emerald breath. Amateur astrophotographers around the world, those dedicated souls who chase photons through cold nights, noted the green tinge too. Some captured it during September's lunar eclipse, when the darkened skies allowed faint objects to shine. Michael Yeager and Gerald Riemann, observing from Namibia's clear deserts, imaged the blue-green coma with exquisite detail, their photographs revealing what larger instruments confirmed: the shifting palette of alien chemistry. Earlier, back in July, Hubble images had shown the reddish dust cocoon clearly, a protective shroud. But later observations from Hubble and ground-based facilities revealed the evolving coma morphology, the changing face. The red dust phase dominated at greater heliocentric distances when the comet was farther from the Sun, cooler, quieter. But the green gas phase emerged closer to perihelion and persisted afterward, revealing the activation of buried material, fresh exposure post-heating, veiled red past unveiling green present. Consider the mechanism. Drift with this understanding. Fluorescence requires solar UV excitation of gas molecules. Without sunlight's ultraviolet touch, the molecules remain dark, invisible. But bathe them in UV and they fluoresce. They glow with their characteristic colours. The dust, by contrast, reflects sunlight broadly, across many wavelengths, but biased toward red by the organic content, those tholins absorbing blue. Gas emissions are line-specific, producing characteristic colours, narrow wavelengths, pure hues. This is why the green appears so vivid, so distinct. It is not reflected light scattered across a spectrum, but emitted light. Photons released at exact energies, molecular green whisper. The coma size grew, expanding from thousands of kilometers across to tens of thousands, a vast envelope of gas and dust, growing, breathing outward. Gas outgassing increased post-perihelion, the rate climbing. Water ice grains contributed to the extended coma glow, sublimating, leaving trails. Carbon dioxide and carbon monoxide dominated the volatile inventory, driving the chemistry, influencing what molecules could form, what colours could emerge. The green glow became visible particularly in green and blue filters post-November, while red filter images still showed the dust component, persistent, the red dust memory lingering even as green dominated the visual appearance. Photochemical reactions drive the molecular excitation, sunlight not merely warming, but breaking bonds, exciting electrons, triggering cascades of chemistry. The fluorescence lifetime is short, requiring continuous UV input. Turn off the sun, and the glow would fade in moments. But the sun shines, patient, constant, and so the molecules keep fluorescing, keep glowing for as long as they remain in the coma, before photodissociation destroys them or they drift too far from the nucleus to be replaced. Coma density affects the visibility of emission colours. Thicker regions glow more brightly, thinner regions fade to darkness, and dust can obscure the gas glow at larger distances. Tholin veil dissolution revealing what was always there, waiting. The closer approach unmasked these gas emissions, brought them into view. The interstellar origin of 3I Atlas preserves, scientists believe, a unique organic inventory. Materials formed in another stellar system, around another sun, processed by different conditions. Cosmic rays from a different galactic neighborhood over billions of years of wandering. Comparisons to 2I Borisov, the previous interstellar comet, show intriguing similarities. Borisov also displayed initial red dust and also developed a green coma later as it approached its own perihelion, suggesting perhaps common processes, common chemistries, despite their different origins, their different births. But Oumuamua, that first confirmed interstellar visitor, showed no coma, no colour shift, because it produced no detectable outgassing, remaining inert, asteroidal perhaps, a mystery of a different kind. The colour evolution of comets like 3I Atlas and Borisov informs outgassing models, helps refine our understanding of how these bodies activate, how heat penetrates, how volatiles escape. Multi-wavelength data tracks these compositional changes, each wavelength a probe, a question asked of the universe. X-ray observations show where the solar wind interacts with the coma, charge exchange producing X-rays, highlighting the extent of the gas, the boundary between comet and space. As the comet begins its long journey outward again, receding from perihelion, the green glow will fade, must fade, as UV excitation diminishes with distance, the square of the distance, light spreading, weakening, until eventually, perhaps, the coma returns to its dust-dominated reddish state, or perhaps dissipates entirely. The dust tail, we notice, remains reddish longer, those particles reflecting sunlight long after the gas has thinned. The ion tail, plasma stripped away by solar wind, may show blue plasma glow, a different mechanism, a different beauty. But the neutral gas coma, that is the primary source of green, diatomic calm radiance in the darkness. Photodissociation produces those daughter molecules we mentioned, parent molecules like methane or formaldehyde, complex organics buried in the ice, breaking apart under UV bombardment, releasing C2, releasing CN. The organic precursors in the nucleus drive these emissions, their abundance, their nature, determining what colours bloom, what signatures emerge. The low carbon chain depletion observed early challenge standard comet models. Most comets show strong C2 emission from the start, but 3I Atlas held back, kept its carbon chains hidden, until perihelion forced them into view, a possible enrichment from its origin system, or perhaps surface processing that sealed away the volatiles more effectively than in solar system natives. The colour change timeline aligns beautifully with the perihelion passage. Pre-October predominantly red, November through December showing greenish dominance, a clear correlation, a story told in hues. The appearance varies depending on which filter observers use. Filter-dependent appearance, reminding us that colour itself is a human perception, a translation of wavelengths into sensation. Visual observers, looking through eyepieces. Note subtle teal or emerald hues, hard to define, easy to feel. Astrophotography stacks enhance colour contrast, combining many exposures, revealing what the eye alone might miss, while professional spectroscopy confirmed the molecular identifications with certainty. Lines in spectra, unmistakable fingerprints. The green signature is common in solar system comets. Nothing rare about C2 emission itself. Hale-Bopp famously displayed a strong C2 green coma, visible even to unaided eyes in 1997, a generation ago now. But in the interstellar context, the shift becomes noteworthy, meaningful, because it reveals how an object formed in another stellar system activates, responds to our sun, shows its buried composition, The surface of 3I Atlas, devolatilized over eons of interstellar travel, cosmic rays and stellar winds slowly eroding, removing volatiles, darkening organics, finally yielded to solar heating, and fresh material from below emerged into sunlight, into fluorescence, hidden fluorescence, peace becoming visible glow. Think of color as a proxy, a messenger, telling us about chemical stratification, layers within the nucleus. The red tells us about surface processes, radiation damage, organic complexity. The green tells us about subsurface volatiles, carbon chemistry, preserved composition. Together they map, in wavelengths rather than kilometers, the structure of this traveler, emerald signature of buried life potential, not life itself, but the chemical complexity that life requires, the building blocks, the possibilities. The implications for extrasolar comet diversity spread outward. Each interstellar visitor teaches us something new, expands our understanding. Dirce-Borisov looked remarkably similar to solar system comets. Oumuamua looked utterly strange, and 3 Atlas. 3 Atlas shows us the transformation, the journey from red to green, dust to glow, shift unfolding over months. The data refines fluorescence efficiency models, improving our equations, our predictions, helping us understand not just these visitors, but comets in general, the physics of gas emission, the chemistry of photodissociation, the optics of scattering and fluorescence. Polarimetry measurements show that the dust properties remained largely unchanged through the color transition. Same particles, same sizes, same compositions. It was the addition of gas, layering over the dust, that altered the overall reflectance, the perceived color, made the coma bluer than sunlight in some post-perihelion data, gas scattering enhancing short wavelengths. The red dust persists in the tail, streaming behind, while the coma head grows greener, a spatial separation, head and tail telling different parts of the story, coma palette evolution visible in single images. Let yourself drift now. Feel the pristine glow integration, the way dust and gas combine, compete, complement. The morphological evolution we see accompanies the color transformation, shape and hue dancing together, and ongoing monitoring continues, will continue, tracking the fading green as the comet recedes, documenting the reverse transformation perhaps. Green fading back to red, glow surrendering to dust, or simply fading to invisibility as the coma dissipates entirely, becomes too faint for even large telescopes to detect. These lessons, these observations, prepare us for future interstellar visitors. There will be more, must be more. The galaxy contains hundreds of billions of stars, countless planetary systems, and objects are occasionally ejected, cast out, to wander. Some small fraction of these wanderers will pass through our solar system, and we will watch, measure, learn. The color transformation of 3I Atlas highlights the dynamic activation process, shows us that interstellar objects are not dead, not inert, but sleeping, waiting, ready to awaken when warmth touches them, when a new sun calls them into fluorescence. The chemical depth revealed through color speaks to formation conditions in that distant system, billions of years ago, around a star we cannot name, cannot see. The organic inventory, the volatile composition, the dust properties, all formed there, processed during the system's youth, ejected perhaps during planetary migration, during the chaotic dance of young worlds, and then silence, cold, drifting through the interstellar medium for eons until our sun's gravity reached out, curved the trajectory, drew the wanderer in, and our warmth woke it, brought colour to its slumber. Interstellar hue drift, from red to green and perhaps back again, tells a story of temperature, distance, chemistry, activation. It is a narrative written in wavelengths, read by spectrographs, interpreted by patient astronomers, and whispered now to you as you sink deeper. The eternal colour stillness that awaits when the comet finally goes dormant again, or disintegrates, or fades beyond detection, is not an end, but a return to the quietude between stars, where colour means nothing, where only darkness and time exist, until perhaps, millions of years hence, another sun, another awakening. Think of the reddish dust, those first observations in July, as the comet showing us its exterior, its armour, its weathered surface. The protective layer built up over time immemorial, and then perihelion, solar kiss igniting quiet verdant fire, breaching that armour, reaching the interior, the pristine material, and the green emerged, not replacing the red, but adding to it, layering, until the composite view showed green dominance, the interior finally visible, chemistry revealed through chromatics, the universe teaching us to read light, to see beyond simple brightness, to understand that colour carries information, carries history, carries the story of where an object has been, what it has endured, what it contains. The journey from red to green, dust veil lifting to reveal hidden gaslight, is the journey of observation itself. First we see the obvious, the exterior, the reflected sunlight. Then, with patience, with careful observation, with the right instruments at the right time, we see deeper, the emissions, the fluorescence, the true nature. Every comet teaches us this lesson, but interstellar comets teach it more dramatically, because they arrive with their surfaces processed by the interstellar environment, by cosmic rays and time, hiding their treasures more effectively, making the eventual revelation more striking, more precious. The transformation happens on human timescales, weeks and months, fast enough to observe, slow enough to track. We watch, we wait, we measure, and the comet reveals itself gradually, surrendering its colours one by one, and in doing so, it connects us to its origin, to that other stellar system we touch through light and spectroscopy, a place we will never visit, a sun we will never orbit, and that connection, mediated by photons and fluorescence, by dust and gas and colour, creates a kind of cosmic intimacy, a sharing across impossible distances. As you breathe slowly now, in and out, imagine you are that photon of UV light travelling from sun to comet, striking a molecule of C2, transferring energy, and being re-emitted as green, as visible light, as the signature colour that telescopes capture. You are the transformation, the energy transfer, the mechanism of fluorescence itself, and in being that, you are part of the story, part of the observation, part of the quiet revelation that science offers. The way careful attention transforms mystery into understanding, red into green, unknown into known, the transformation that science itself represents, the patient translation of wavelength into meaning, of colour into chemistry, of observation into understanding. Sink deeper now. Let the weight of your body dissolve, and consider how the coma's appearance shifts depending on which instruments observe it, which filters are selected. A telescope equipped with a red filter sees primarily the dust component, the scattered sunlight, the particles drifting outward, painting a picture of the solid material ejected from the nucleus. But switch to a green filter, a blue filter, and suddenly the gas emissions dominate. The fluorescence overwhelms the scattered light, revealing an entirely different landscape, a landscape of molecules rather than particles, of emission rather than reflection. This is the power of wavelength selection, of asking the right questions in the right way. Each filter is a question, and the comet answers differently each time, truthfully each time, but showing different aspects of its nature. The composite images, combining red, green, and blue exposures, create something closer to what a human eye might see. Though of course no human eye can gather light for minutes or hours the way cameras cannot integrate photons with such patience. The overall greener tint in post-November composites tells us that gas emission has become the dominant source of light in the coma, that molecular fluorescence outshines dust reflection, at least in certain wavelengths, at certain distances from the nucleus. The balance shifts, tilts, toward the green, toward the living emerald breath of diatomic carbon. Let your mind wander now through the scale of what we're describing. The coma grew from thousands of kilometers across to tens of thousands. Imagine a cloud larger than Earth, larger than Jupiter, a tenuous atmosphere of gas and dust surrounding a nucleus perhaps only a few kilometers in diameter. The nucleus itself, that solid body, that dirty snowball, is invisible to us, hidden within the vast envelope it creates. We see only the consequences of its sublimation, the cloud it exhales, the colours it paints across space. The actual comet, the rock and ice, remains a mystery, inferred but never directly observed, too small, too faint, too embedded in its own atmosphere. The dust tail, that elongated structure stretching away from the sun, remains reddish longer than the coma. This makes sense when you consider the physics. Dust particles, once ejected, continue on ballistic trajectory, falling away from the sun's radiation pressure. They carry with them the organic coating, the tholins, that give us their ruddy colour, and they're not being continuously replenished with new material the way the coma is. The coma, constantly fed by sublimation from the nucleus, constantly refreshed with new gas, can change composition quickly. But the tail, stretching millions of kilometers behind, represents material ejected hours or days or weeks ago, a historical record, a timeline written in particles. The older material at the tail's far end may still look as it did in July, still red, still dust-dominated, while the near-nucleus regions glow green with fresh gas. There's something deeply peaceful about considering the ion tail, which may show blue plasma glow, a different mechanism entirely. Here we're not talking about dust or neutral gas, but ionized particles, charged molecules stripped of electrons by the solar wind. These ions follow magnetic field lines, flow away from the sun in straight structures, and where they recombine with electrons, when charge exchange occurs, they emit light at different wavelengths than neutral gas fluorescence, often in the blue, sometimes in pink or violet, depending on which ions dominate: carbon monoxide ions, water ions, each with their signature, but the neutral gas coma, that's what gives us the green, that diatomic carbon, those cyanide radicals, swimming in the space around the nucleus, glowing continuously as long as sunlight touches them. The production rate of these molecules, measured by observing the brightness of their emission lines, increased dramatically after perihelion spectroscopy, that patient dissection of light into its component wavelengths, revealed the strengthening signatures, the swan bands of C2. Those characteristic green emissions between 510 and 560 nanometers grew brighter, more prominent, while the CN violet system, emitting around 380 to 390 nanometers, showed its own intensification. These are not arbitrary numbers. They are fundamental properties of these molecules, the exact energy differences between electronic states, quantum mechanics made visible, the universe revealing its mathematics through color. Consider the journey of a single carbon-bearing molecule buried in the nucleus. Perhaps since the comet's formation billions of years ago, it sits frozen, motionless, at temperatures near absolute zero. For eons, cosmic rays occasionally strike it, break bonds, create new structures, but mostly silence, cold, stillness. Then, our sun's warmth begins to penetrate. The outer layers sublimate away, dust and simple volatiles escaping first, and finally, the layer containing our molecule reaches the surface, heats, transitions from solid to gas, and erupts into space. Suddenly, motion, expansion, and then ultraviolet light. Solar photons strike the molecule, excite electrons to higher energy states, and when those electrons fall back down, the molecule emits a photon of green light. Our telescope captures that photon, adds it to millions of others, and we see the green glow. We see the biography of that molecule written in a single wavelength. The fact that C2 emission was not detected early, that it appeared only after perihelion, tells us something profound about the comet's structure. Its surface had been depleted of carbon chains, either through sublimation during previous passages near other stars, unlikely given the interstellar trajectory, or through processing by cosmic rays over billions of years, or perhaps the original formation process created a layered structure, carbon-poor exterior, carbon-rich interior. When we finally saw the green, we were seeing deeper material, freshly exposed. This is chemistry as archaeology. Each layer a different epoch, each colour a different chapter in the comet's history. Breathe slowly and think about the timescales involved. The comet's formation, billions of years ago, around a star that may no longer exist, may have gone supernova or simply faded to a white dwarf. The ejection from that system, perhaps hundreds of millions of years ago during some gravitational upheaval. The journey through interstellar space, cold, dark, silent, for longer than complex life has existed on Earth. And then, our sun's gravity, reaching out across light years, gradually bending the trajectory, drawing the wanderer in, the final approach. Months compressed from eons, and the transformation, red to green, happening in weeks. A story that spans the age of stars as culminating in a colour change we can watch in real time. The comparison to other objects enriches our understanding. When we compare 3I Atlas to solar system comets, we find both similarities and differences. The green C2 emission is common, expected. Comet Hale-Bopp in 1997 displayed a magnificent green coma visible to anyone who looked up. That green became iconic, appeared in photographs around the world, became synonymous with comet for a generation. But Hale-Bopp was a solar system native, had passed through the inner solar system before, would do so again in thousands of years. Its carbon was not buried. Its emissions began early and stayed strong. 3 Atlas, by contrast, surprised us by waiting, by keeping its green hidden until perihelion forced it into view. This delayed revelation, this surprising emergence, makes the transformation more dramatic, more meaningful. And Borisov, 2I Borisov, that previous interstellar comet discovered in 2019, showed a similar pattern, initially dust-dominated and reddish, then developing a green coma as it approached perihelion. This parallel suggests, perhaps, that interstellar comets generally have surfaces processed by the interstellar medium, devolatilized, sealed, until solar heating breaks through. Or perhaps it's simply that we're observing them at large distances initially, where dust naturally dominates and gas emission becomes visible only closer in. But the pattern holds. Interstellar comets awaken slowly, reveal their greens reluctantly, as if they've forgotten how to respond to starlight after so long in darkness. Oumuamua, strange Oumuamua, showed no coma at all, no colour change, no outgassing. It accelerated oddly, suggesting something escaping from its surface, but nothing visible, no dust, no gas, no colours beyond the red of its surface. It remains an enigma. Possibly a comet with volatiles too deeply buried to escape. Possibly something else entirely. An alien artifact. Some whisper, though that seems unlikely. Probably just an unusual icy body with a very thick crust. But its silence, its lack of transformation, makes the colour changes of Borisov and 3I Atlas more precious, more appreciated. They awaken, they transform, they share their chemistry with us. The multi-wavelength observations, combining visible light, ultraviolet, X-ray, paint a complete picture. X-rays reveal where the solar wind, that stream of charged particles flowing outward from the sun, collides with the neutral gas coma. In this collision, charge exchange occurs. Ions from the solar wind steal electrons from neutral molecules, and in the process, emit X-rays. This creates an X-ray glow around the coma, invisible to our eyes, detectable only with space-based X-ray telescopes. The size of this X-ray emission region tells us about the extent of the gas, about how far the neutral coma reaches. It's another way of seeing, another question asked, another answer given. Ultraviolet observations are particularly valuable because they see the solar radiation that causes the fluorescence. They see the input, the cause, while visible light observations see the effect, the output. By measuring both, we can calculate fluorescence efficiencies, how effectively different molecules convert UV light into visible emission. These efficiencies depend on molecular structure, on quantum mechanical selection rules, on the specific energy levels available, and they vary. C2 is very efficient, which is why it glows so brightly green even when not particularly abundant. Other molecules may be more abundant but less efficient, visible only to spectroscopy, not to color imaging. The photodissociation lifetime of these molecules, how long they survive in sunlight before breaking apart, is short. For C2, measured in hours, perhaps a day, near the sun. This means the green glow requires continuous production, continuous sublimation from the nucleus. If the outgassing stopped, the green would fade within a day or two. This gives the coma a kind of immediacy, a real-time quality. What we see reflects what's happening now, not what happened weeks ago. The coma is the present tense of the comet, while the tail is past tense, stretching behind, a memory, a history. Let yourself feel the rhythm of this process. Sublimation, ejection, excitation, emission, decay. A continuous cycle. As long as sunlight warms the surface, as long as volatiles remain to escape, the nucleus rotates. Perhaps once every few hours or days. We don't know the exact period for 3i Atlas, presenting different regions to sunlight. Some regions may be more active than others, richer in volatiles, creating jets, outbursts, asymmetries in the coma. But averaged over time, smoothed over the rotation, we see the overall emission, the average color, the general transformation from red to green, the polarimetry measurements, analyzing how light is polarized when it scatters off dust, revealed that dust properties stayed consistent. The particle sizes didn't change dramatically. The compositions remained similar. The structure of individual grains stayed constant. This tells us that the color change wasn't due to changing dust properties, wasn't caused by dust grains growing or shrinking or changing composition. Instead, it was purely an addition, a layering, gas emission adding to dust reflection, eventually dominating it, eventually outshining it in certain wavelengths. The dust remained patient, constant, red, but the green gas grew brighter, louder, until it shouted down the whisper of scattered dust light. Some post-perihelion observations showed the overall spectrum bluer than sunlight, bluer than would be expected from pure reflection. This is gas scattering at work, Rayleigh scattering, the same physics that makes Earth's sky blue. Shorter wavelengths scatter more efficiently than longer ones. The green and blue emissions from fluorescence, combined with this preferential scattering, shifts the overall color toward shorter wavelengths, toward the blue-green, teal, emerald. The exact shade depends on viewing geometry, on which part of the coma you're observing, on the density of gas versus dust. But the trend is clear. Gas makes the comet bluer, greener, more vibrant in a way, while dust keeps it reddish, earthy, muted. The spatial separation becomes visible in detailed images. The coma head, the region immediately surrounding the nucleus, glows green with active gas emission, fresh material sublimating constantly, fluorescence immediate and strong. But the tail, stretching behind for millions of kilometers, remains predominantly red, dust particles drifting, reflecting, no longer actively producing gas. This creates a beautiful gradient in color images, green at the center, transitioning to yellow-green in the middle coma, to yellow-orange in the near tail. to red-orange in the far tail, a spectrum painted across space, a rainbow of transformation, showing the progression from active emission to passive reflection, from present to past, from green to red. Drift now through the implications for planetary science, for astrobiology, not because these comets carry life, they don't, but because they carry complexity. Carbon chains, organic molecules, cyanide. These are precursors, building blocks, the chemistry happening in the coma, driven by sunlight, by photodissociation, by reactions in the gas phase. This mimics chemistry that may have occurred in the early solar system, that may have seeded Earth with organic compounds. Every comet is a laboratory, every coma an experiment in prebiotic chemistry, and interstellar comets, formed in different conditions, around different stars. Add to the sample size, add variety, help us understand not just our own origins, but the range of possibilities, the diversity of chemical pathways that might lead, eventually, to life. The specific molecules detected, C2, CN, even simple ones like OH hydroxyl radicals from water dissociation, tell us about the parent molecules in the ice. We don't directly observe methane or methanol or formaldehyde. They dissociate too quickly, but we see their children, their fragments, and from these fragments we infer the parents. It's detective work, chemistry in reverse, taking the products and working backward to the ingredients, and each molecule adds a piece to the puzzle. C2 suggests carbon-rich organics, CN suggests nitrogen-bearing compounds, HCN perhaps, or more complex nitriles. O tells us about water ice, which we expected, but confirms our models, validates our assumptions. The temperature of the nucleus surface, estimated from the activity level, from the sublimation rates, reach perhaps 200 to 250 Kelvin near perihelion, still far below the freezing point of water by Earth standards, but warm enough to sublimate carbon dioxide, carbon monoxide, methane, other volatiles. Water ice sublimates too at these temperatures, slowly, adding to the outgassing. The temperature gradient within the nucleus, warmer at the surface, cooler just beneath, coldest at the center, creates the layered activation we observe. First, the surface volatiles, then deeper layers as heat penetrates. The transformation from red to green maps this thermal gradient, this wave of warmth, moving inward, awakening sleeping chemistry layer by layer. Consider the cosmic ray processing that occurred during the interstellar journey. High energy particles are protons, helium nuclei, striking the surface, penetrating micrometers, breaking chemical bonds, creating radicals, driving chemical reactions even at near zero temperature. Over millions of years, this processing could significantly alter the surface composition, destroy volatile ices, create complex organics, darken materials. This is why the surface appeared dust-rich and reddish initially, why volatiles were depleted. The cosmic rays had done their work, patient, thorough. Over timescales we can barely comprehend, but they penetrate only so far, millimeters at most. Below that, pristine material, unchanged since formation, waiting. The rotation of the nucleus, though not precisely measured for 3i Atlas, affects the color we observe. If the nucleus rotates rapidly, every few hours, Then different regions face the sun in quick succession, and the colour we see is a time average over many different surface compositions. But if it rotates slowly, days or weeks, then we might be observing the same hemisphere for extended periods, seeing a more stable colour, more consistent emissions. The light curve, how brightness changes over time, would reveal rotation, but requires many observations, careful photometry, patience. Some asteroids rotate in minutes, some in months. Comets likely fall in the middle range, hours to days, but each is unique, each has its own rhythm. The outgassing itself is not uniform, not symmetrical. Jets of gas, focused streams, erupt from active regions, areas where volatiles are particularly abundant or where sunlight strikes more directly. These jets can push the nucleus, change its rotation, alter its orbit slightly. This non-gravitational acceleration was detected for 2I Borisov, small but measurable. For 3I Atlas, the trajectory was measured carefully, looking for similar effects. These tiny pushes, these whispers of gas pressure, tell us about the distribution of activity, about whether outgassing is uniform or concentrated, about the shape and rotation state of the hidden nucleus, the dust-to-gas ratio. How much dust is ejected per unit of gas is a fundamental parameter characterizing the comet's nature. Dust-rich comets, high ratio, appear redder, produce prominent dust tails. Gas-rich comets, low ratio, appear greener, produce fainter dust tails but strong ion tails. 3I Atlas appeared to transition from high dust to gas early to lower dust to gas later, as if the surface dust layer was being stripped away, revealing more volatile-rich material beneath. This transition in ratio contributed to the colour change. Early observations saw mostly dust. Later observations saw relatively more gas. The actual amounts of both dust and gas increased, but gas increased faster, shifted the balance, tilted the colour toward green. Imagine the moment of perihelion itself. October 2025, the closest approach, maximum solar heating, maximum activity. The surface temperature peaked, sublimation rates maximized, gas production surged. This was the crisis, the climax, the moment of transformation. And in the weeks that followed, as the comet began receding, the green became most visible, most dominant, because the surface crust had been breached, the volatile layers exposed, and even though solar heating was declining, access to those volatiles remained. The green persisted, faded gradually rather than shutting off suddenly. The comet had been changed by perihelion, opened, wounded perhaps, or liberated, depending on your perspective, and it would not quickly seal itself again. The comparison of telescope observations from different locations, Gemini North in Hawaii, VLT in Chile, Hubble in space, amateur observers from every continent, creates a global portrait, a planetary collaboration. Each observer adds data, adds perspective. Space-based observations avoid atmospheric absorption, see ultraviolet wavelengths blocked from the ground, but have limited observing time. Ground-based telescopes can observe for hours, track changes, but must contend with weather, atmospheric turbulence, light pollution. Together, combined, they create a complete picture that no single observatory could achieve alone. This is modern astronomy. collaborative, distributed, each contribution valuable. The spectral resolution, how finely wavelength is measured, determines what details can be seen. Low-resolution spectroscopy, a few hundred spectral channels across the visible range, can identify strong emission lines, distinguish gas from dust, measure rough abundance ratios. High-resolution spectroscopy, thousands or tens of thousands of channels, can resolve individual molecular lines, measure Doppler shifts from gas motion, determine temperatures from line widths. Each level of detail reveals different information, answers different questions. For sleep tonight, we don't need the highest resolution, the finest details. We need only the broad story, red to green, dust to gas, transformation, revelation. The green will fade, is fading already as the comet recedes. As of December 2025, moving outward, growing fainter, the green remains visible but weakening. The UV flux decreases with the square of solar distance twice as far. 1/4 the UV, 4 times as far, 1/16. The fluorescence efficiency stays the same, but the excitation rate plummets, and simultaneously, gas production decreases, cooler temperatures, less sublimation, fewer molecules to fluoresce. The combination, less gas, less excitation, drives the fading. Eventually, perhaps early 2026, the green will become undetectable. The comet will be too faint, too far, too quiet. It will return to darkness, to silence, carrying its remaining volatiles back into the interstellar void, its transformation complete, its story told. For this passage, this brief encounter with our sun, this moment of awakening in a journey that spans eons. Let your thoughts slow now, soften, as you contemplate the cycle, formation, ejection, wandering, approach, awakening, transformation, recession, return to cold. This is the pattern, the rhythm, the universal story of interstellar comets, and likely of planets too, of moons, of all objects that travel between stars. They carry with them the signature of their birth, modified by their journey, briefly illuminated by a foreign sun, and then back to darkness, changed but recognizable. Memory holders, ambassadors, teachers, showing us that the universe is not static, not isolated, but connected, flowing, objects and information moving between stellar systems, between epochs, between chemical regimes. The green glow of 3i Atlas is a message, written in fluorescence, delivered across light years, telling us that chemistry is universal, that transformation is inevitable, that colour, simple colour, can reveal histories longer than civilizations, deeper than oceans, more ancient than mountains. Breathe deeply, slowly, and feel yourself becoming like the comet, transforming, shedding one state for another, releasing what no longer serves, allowing what was buried to emerge, the red of day, of activity, of surface concerns, giving way to the green of rest, of emission, of deeper truth. You are sublimating stress, outgassing worry, creating your own coma of peace, of quietude. And in this transformation, this colour change, you're engaging in your own cosmic process, your own journey from one state to another, from waking to sleeping, from thinking to dreaming, from red to green, from dust to glow, from noise to silence, from complexity to simplicity, from the many to the one. Let this transformation wash over you, gentle as starlight, inevitable as gravity. The images captured by amateur astrophotographers, those dedicated observers working through cold nights with backyard telescopes, revealed nuances that even large professional instruments sometimes miss. Michael Jaeger and Gerald Riemann, observing from Namibia's dark skies, captured the blue-green coma with stunning clarity in their long exposures, stacking dozens or hundreds of images, aligning them perfectly, bringing out colours invisible to the unaided eye. Their work, shared freely online, allowed people around the world to witness the transformation, to see the green emerging. These citizen scientists, passionate volunteers, contribute meaningfully to our understanding. Their images complement professional observations, add temporal coverage, provide different perspectives and equipment sensitivities, proving that cosmic discovery is not limited to those with the largest telescopes, but open to anyone with patience, dedication, and dark skies. During September's lunar eclipse, when the moon's shadow darkened Earth, blocking the moon's brightness, faint objects became more visible. Some observers noted a subtle green tinge to 3i Atlas even then, before perihelion, suggesting that gas emission was beginning earlier than initially detected, that the transformation was gradual, not sudden, a gentle transition rather than an abrupt change. This is often how nature works, not in sharp boundaries but in gradients, in zones of mixing, in transitions that blur the line between before and after. The eclipse gave observers a gift, a darker sky, and the comet revealed in that darkness a hint of what was to come, a preview of its green future, a whisper of buried carbon awakening. The Hubble Space Telescope images from July, those early observations showing the reddish dust cocoon, have historical value now. They document the before state, the baseline against which all later observations are compared. Hubble's sharp vision above the atmosphere captured details of the inner coma structure, possible jets, asymmetries. The nucleus remained unresolved, too small even for Hubble at that distance. But the immediate surroundings revealed activity patterns, dust distribution, coma morphology. These early images, combined with the later ground-based observations showing green, create a before and after story, a documented transformation, evidence captured in pixels and photons, archived for future study, for future questions we haven't yet learned to ask. The archiving of observations, this practice of preserving data, creates a legacy that extends beyond immediate discovery. Future astronomer, decades or centuries from now, may return to these images of 3i Atlas, may reprocess them with techniques not yet invented, may ask questions we haven't conceived, and find answers waiting in the photons captured in 2025. This is the gift of digital astronomy. Data persists, waits patiently, ready to be interrogated again and again. Each pixel holds information, some extracted immediately, some remaining latent, hidden until the right question unlocks it. The comet has come and gone, but its light, captured and stored, remains, a kind of immortality, a presence that outlasts the presence. Let your breathing deepen, slow, as we consider the filters themselves, those carefully crafted pieces of glass or interference coatings, each designed to pass only specific wavelengths, to ask only specific questions. A green filter, typically centered around 500 to 550 nanometers, isolates the C2 emission, sees the diatomic carbon glow, excludes the rest. It's like listening to a single instrument in an orchestra. The comet plays many wavelengths, produces a full spectrum, but the filter lets us hear just one voice, just one color. This selective listening, selective seeing, reveals structure invisible to broadband observation, shows that the coma is not uniform in color, not homogeneous, but layered, varied, different regions dominated by different emission mechanisms. The blue filters, shorter wavelengths, around 400 to 500 nanometers, capture the CN emissions, the cyanide radicals contributing their blue-green tones, and also catch some of the scattered sunlight, which is itself bluish at short wavelengths. The combination creates images that look different from green-filtered ones, showing different spatial structures, different brightness distributions. The tail may appear fainter in blue, the inner coma brighter, because CN production is strongest close to the nucleus, where parent molecules freshly sublimate and quickly photodissociate. Further out, CN may be depleted, destroyed by further photodissociation or reactions. The spatial distribution of color, where green dominates versus where blue dominates, maps the chemistry, maps the timescales of molecular processes, and the red filters, around 600 to 700 nanometers, see primarily scattered sunlight from dust. They show the particles, the solid material, the tholin-coated grains drifting outward. In post-perihelion images, when green and blue filters show bright gas emission, red filters still reveal the dust component, quieter, more subtle, but persistent. The dust tail remains visible in red when it fades in other colors. This is because dust reflects light at all wavelengths, but the red is less contaminated by gas emission lines, less overwhelmed by fluorescence. It shows the skeleton, the underlying dust structure, upon which the gas emissions are layered. Orange filters, intermediate wavelengths, around 550 to 600 nanometers, capture a mixture, some gas, some dust, a blended view. In the spectrum of comets, this region contains some C2 bands, some dust continuum, various minor emission lines. The orange appearance in some images represents this mixture, this transition zone in wavelength space, between gas-dominated shorter wavelengths and dust-dominated longer wavelengths. It's a reminder that nature doesn't divide neatly, doesn't separate cleanly into categories we create. The comet emits and reflects continuously across the spectrum, and our filters carve that continuum into discrete pieces for analysis, for understanding. But the reality is continuous, flowing, unbroken. Consider now the photometric measurements, the careful quantification of brightness. Astronomers measure the comet's magnitude, its brightness as it would appear to a standard observer, and track how this changes over time. The brightness increased as the comet approached perihelion, peaked around closest approach, and now fades as it recedes. This light curve, brightness versus time, contains information about the outgassing rate, the dust production, the activity level. By fitting models to the light curve, scientists can estimate how much material sublimates each second, how much energy the comet receives and re-radiates, how efficiently it converts solar heating into activity. The color indices, differences in magnitude measured through different filters, quantify the color change. A B-V index, blue magnitude minus visual magnitude, becomes more negative as the comet gets bluer, gets greener. This numeric measure, this single number, captures what we see qualitatively, the shift from red to green, and allows precise comparison across different observation dates, different observatories, different instruments. Numbers remove ambiguity, remove subjective interpretation, though they also remove, in a sense, the immediate aesthetic appreciation, the simple beauty of green glow against black space. Science trades immediacy for precision, gains understanding at the cost of wonder, though perhaps, for some, understanding generates its own wonder, deeper, more durable. Drift now with the concept of signal-to-noise ratio, how faint signals emerge from background noise. The comet, especially at large distances, is faint, very faint. Its light competes with sky brightness, with the glow of our own atmosphere, with light pollution from cities, with the faint background of unresolved galaxies and stars. Long exposures help, stacking many images helps, but there's always noise, random fluctuations, cosmic rays striking the detector, electronic noise in the readout. The green emission, when it appeared, had to rise above this noise, had to be confidently detected, not just a fluctuation, not just wishful seeing. Spectroscopy confirms, provides certainty, shows the emission line at the exact expected wavelength. Unmistakable, real, not noise but signal, not accident but reality. The gas production rate, measured in molecules per second, increased from perhaps 10 to the 26 molecules per second in early observations to 10 to the 27 or even 10 to the 28 near perihelion. These numbers, so large as to be almost meaningless, represent quadrillions of molecules escaping every second, sublimating from the surface, expanding outward, filling the coma. Some are water, H2O, some carbon dioxide, CO2, some carbon monoxide, CO, and smaller amounts of other species, methane, ammonia, various organics. The exact composition varies with depth, with location on the nucleus, with temperature. Early in the approach, only the most volatile ices sublimate, CO escaping even from cold surfaces. Later, closer to perihelion, warmer surfaces, less volatile species join. Water begins flowing, organics pyrolyze, break apart, release their constituents. The nucleus itself, that hidden core, is estimated to be perhaps 2 to 5 kilometers in diameter, maybe larger, maybe smaller. We cannot see it directly, cannot resolve it, but we can infer its size from the total mass ejected, from the brightness, from comparisons to other comets. A few kilometers, small enough to fit within many cities, small enough to walk across in an hour or two, yet containing enough volatiles to create a coma hundreds of thousands of kilometers across, enough material to sustain activity for months. The efficiency is remarkable, nearly all the surface actively sublimating when heated, little wasted, little inert. This is the nature of comets, efficient transformers of heat into activity, of solar energy into kinetic energy of escaping gas and dust. Let yourself feel the scale dissolving, the nucleus, kilometers, the coma. hundreds of thousands of kilometers, the tail, millions of kilometers, and the journey, trillions of kilometers across interstellar space before arriving here, each scale nested within the next, like Russian dolls, like fractals, pattern repeating at different magnifications. And you, observing this, thinking about this, drifting through this, are part of the larger scale, consciousness in the universe contemplating the universe, awareness arising from stellar alchemy, carbon and oxygen and nitrogen formed in stars, now forming thoughts about carbon and oxygen in a comet. The recursion is beautiful, dizzying, peaceful in its circularity. The thermal inertia of the nucleus, how quickly it heats and cools, affects the outgassing pattern. A body with low thermal inertia, like loose dust or porous ice, heats quickly when sunlight strikes, cools quickly when darkness comes or when the sun's angle changes. This creates rapid changes in activity, bright jets when directly illuminated, quieter periods in shadow. A body with high thermal inertia, like solid rock, heats slowly, retains heat, continues outgassing even after sunset on its surface. Comets typically have low thermal inertia, porous structures, fluffy, allowing rapid thermal response. This means outgassing can vary substantially over a rotation period, over hours, as different regions face the sun. The dust grains themselves, those particles we've mentioned, have their own story. Each grain began as a tiny mote, perhaps in the protoplanetary disk, condensing from vapor, accreting layer by layer, organic coatings depositing, silicates incorporating, metals mixing in. The final grain, micrometers across, contains memory of formation, carries isotopic signatures, trapped noble gases, organic complexity. When ejected from the nucleus, the grain embarks on its own journey, pushed by gas drag initially, then by radiation pressure from sunlight, light itself. Photons carry momentum, and billions of photons pushing on a small grain create measurable force, driving the grain outward, away from the sun, creating the dust tail. The smallest grains, sub-micrometer size, are pushed fastest, curve away most dramatically. The largest grains, tens of micrometers, are pushed slowly, follow trajectories closer to the nucleus orbit. This size-dependent behavior creates the fan-shaped tail, smaller grains spreading wider, larger grains staying closer to the projected orbit. Think about the organic molecules coating these grains. Tholins, we've named them, but that name encompasses vast complexity. Thousands of different molecular structures, carbon chains, aromatic rings, functional groups containing oxygen, nitrogen, sulfur. These organics formed through radiation processing, yes, but also through cold chemistry in the protoplanetary disk, through reactions in icy mantles on grain surfaces, through photochemistry in the comet's previous activity, if it had any. Each tholin molecule is unique, but the ensemble, the collective, produces consistent properties, consistent colors, consistent spectral signatures. This is emergence, individual complexity producing collective simplicity, many unique molecules behaving as one substance, with one color, one set of properties. The absorption of blue light by tholins, the process that enhances the red color, occurs because certain molecular bonds, certain electronic transitions, absorb preferentially at shorter wavelengths, blue photons, higher energy, are absorbed by the organic molecules, exciting electrons, breaking weak bonds, driving slow chemistry even in the solid state. Red photons, lower energy, pass through, scatter, reflect, and reach our telescopes. This is why the dust appears red, not because it emits red light, but because it removes blue light, leaving red behind. It's a subtractive process, a filtering. The dust acts as a filter itself, selecting wavelengths, changing the color of sunlight that passes through or reflects from the coma. Drift deeper, feeling your own thoughts becoming simpler, more fundamental, like wavelengths rather than complex narratives. The color of scattered light depends on particle size. Rayleigh scattering, when particles are much smaller than the wavelength of light, scatters short wavelengths strongly. This is Earth's blue sky, tiny air molecules scattering blue sunlight. But when particles approach the wavelength of light in size, several hundred nanometers, me-scattering dominates, and the wavelength dependence weakens. The dust grains in the coma, several micrometers, are much larger than visible wavelengths, so they scatter all wavelengths somewhat equally. But the organic coating still absorbs blue preferentially. The combination, size-dependent scattering plus wavelength-dependent absorption, creates the overall color we observe. The concept of albedo, reflectivity, matters too. Cometary dust has low albedo, reflects only a small fraction of incident sunlight, perhaps 4 to 6%. Most light is absorbed, converted to heat, which drives further sublimation. This is a positive feedback. More sunlight absorbed, more heating, more sublimation, more dust ejected. But the dust has such low albedo, such dark color, that even modest amounts create visible brightness. Each grain, though dark, contributes photons, and billions of grains together create the observable coma. The darkness of the dust, its low reflectivity, tells us about composition, carbon-rich materials, organics, perhaps some iron sulfide. Materials that absorb rather than reflect, materials that transform light into heat rather than returning it to space. Your breath now so slow, so gentle, like the slow rotation of the nucleus, turning, presenting different faces to the sun. The rotation period, unknown for 3i Atlas specifically, is typically hours to days for comets. Some rotate in 4 hours, some in 40, some in weeks. The rotation affects observation. A rapidly rotating nucleus presents constantly changing activity, changing brightness, pulsing, while a slowly rotating one appears more stable, changes occurring over days rather than hours. Observers measure these variations, construct light curves, deduce rotation rates, infer shapes. Elongated nuclei show stronger brightness variations than spherical ones. Their changing cross-section modulating the reflected light and the active surface area. The moment when green first became detectable, September perhaps, or early October, marked a transition point, a threshold crossed. Before that moment, C2 production was below detection limits, too faint, too overwhelmed by dust brightness. After that moment, it rose above the noise, became measurable, grew stronger day by day. This threshold, this emergence, is like dawn. Not sudden but gradual, imperceptible until suddenly obvious. The human eye cannot see individual photons arriving, cannot watch emission lines strengthen one photon at a time. We see only the integrated effect, the accumulated signal, and suddenly recognize green where before there was only red. The transition feels sudden, but it was continuous, smooth, just crossing our perceptual threshold at a specific moment. The coordination of observations across the globe, across multiple observatories, creates continuous coverage. As Earth rotates, one observatory sets, another rises. The comet remains observable almost continuously from somewhere. This global network, informal but effective, ensures that rapid changes, outbursts, sudden brightenings are captured, not missed in gaps between observation sessions. Amateur astronomers contribute significantly to this coverage. Their smaller telescopes, their flexibility, their passion, filling temporal gaps that scheduled professional observations cannot cover. The result is a more complete record, a more thorough documentation than any single observatory could achieve. Collaboration, distributed effort, creates understanding greater than the sum of individual observations. Let the understanding wash over you like waves, each wave bringing another detail, another connection. The C2 molecules in sarcoma. We've discussed their fluorescence, but consider their origin more deeply. They come from larger organic molecules, perhaps polyacetylene chains, perhaps aromatic compounds, perhaps formaldehyde polymers. These parent species, solid in the nucleus ice, sublimate when warmed, enter the gas phase, and immediately face the harsh environment of space. Solar UV photons strike them within seconds, break bonds, fragment the molecules. Among the fragments, C2, small, stable enough, abundant. It's a daughter molecule, a child of photodissociation, and it in turn, if given time, will be destroyed, photodissociated into individual carbon atoms. But its lifetime, hours to days, is long enough for it to fluoresce, to glow green, to announce its presence before vanishing. The quantum mechanics of this process, electrons occupying specific energy levels, jumping to higher levels when a UV photon is absorbed, then falling back down. Emitting a visible photon is the fundamental mechanism, quantum mechanics. That strange theory, where particles are waves, where uncertainty is fundamental, where observation affects reality, underlies every color we see in the universe, every green glow, every red sunset, every blue sky, is quantum mechanics made visible. The comet doesn't know it's demonstrating quantum theory, doesn't care, but it does so nonetheless, faithfully, perfectly, following laws it has no choice but to follow, and we, watching, measuring, understanding, recognize those laws, see the mathematics written in light. This is what it means to understand nature, to see the principles underlying appearance, to find universality in specifics. Rest now in this understanding. Let it support you like water. You float in comprehension, in the deep knowledge that everything connects, that colors relate to chemistry, that chemistry relates to quantum mechanics, that quantum mechanics relates to the structure of reality itself. The comet's green glow, simple, beautiful, is also profound, also fundamental, also a doorway to deeper understanding. And you need not understand every detail, every equation, to appreciate the wholeness, the completeness, the way it all fits together. Simply knowing it fits that there are no contradictions, no mysteries that cannot eventually be solved, brings peace, brings restful acceptance, brings the quiet confidence that the universe makes sense even when we don't fully grasp it. The concept of a dust cocoon is beautifully descriptive. The nucleus, the solid body, wrapped in its own exhaled material, surrounded by particles it has shed, cannot be seen directly, only inferred like a chrysalis, though this metaphor breaks down because comets don't emerge transformed. They simply reveal what was always inside. The cocoon is temporary, seasonal, dependent on solar distance and activity level, at great distances, cold and quiet. No cocoon exists. The nucleus sits bare in space, inert, just a dark rock, frozen ice. Then as the sun approaches, warmth builds and the cocoon forms, grows, expands, until the comet is invisible within its own atmosphere, its own creation. Consider the water ice grains, not molecules yet, but tiny crystals, solid particles, sublimating, contributing to the extended coma glow. Water ice reflects sunlight, scatters it, adds to the overall brightness, and as these grains sublimate, transitioning from solid to gas, they absorb heat, cool their surroundings, affect the thermal balance of the coma. This is evaporative cooling on a cosmic scale. The phase change, solid to gas, requires energy, latent heat, and that energy comes from sunlight, from the thermal environment. The process is self-regulating in a way. More sublimation, more cooling, less sublimation, more heating, until equilibrium is reached, until the rate of energy input matches the rate of energy absorption by sublimation. The carbon dioxide and carbon monoxide that dominate the volatile inventory. These drive much of the activity. They sublimate at lower temperatures than water. CO sublimates even far from the sun, at distances where water remains frozen. This creates a natural sequence of activation. First CO, creating early activity, then CO2, then finally water as the comet gets very close and warm. Each volatile contributes differently. CO provides velocity, escape speed, carries dust grains efficiently. CO2 contributes brightness, abundance. Water adds mass, duration. The mixture determines behavior, and 3i Atlas, like most comets, carries all three, creating a complex, layered outgassing profile that changes with distance and time. The photochemistry, the reactions driven by light, occur continuously in the coma. Molecules absorb UV photons, break apart, recombine, create new species, destroy others. The coma is not static but dynamic, a constantly changing chemical reactor. Parent molecules from the nucleus, methane, methanol, ammonia, various organic compounds, break apart within seconds or minutes of entering sunlight. Their fragments, the daughter molecules, react further, producing the species we observe: C2, Cn, O, C3, NH. Each generation of molecules, each step in the cascade, has its own lifetime, its own chemistry. The coma we see is the sum, the integral of all these processes happening simultaneously at different rates in different regions. A chemical symphony, each molecule playing its note, the combination creating the overall colour, the overall appearance. Let your awareness drift outward now, beyond the comet, to the space it travels through. The interstellar medium, not empty, but filled with atoms and molecules, dust grains, magnetic fields, radiation, incredibly tenuous, a few atoms per cubic centimetre on average, but present nonetheless, during its millions or billions of years wandering between stars. 3i Atlas moved through this medium, encountered it, was shaped by it. Cosmic rays, high-energy particles accelerating through interstellar space, struck the surface, penetrated, altered chemistry. This processing, this radiation damage, created the devolatilized surface layer we observed initially, the red tholin-rich crust. The interstellar medium is not kind to ices, not protective. It erodes, it processes, it ages. Over eons, exposed ice sublimates even in the cold, struck by occasional photons from distant stars, occasional impacts from atoms, slowly, so slowly, but continuously, wearing away, darkening until the surface becomes depleted, sealed, quiet. The possible enrichment from the comet's origin system. The stellar system where it formed raises fascinating questions. Different stars have different metallicities, different abundances of elements heavier than hydrogen and helium. A comet forming in a metal-rich system might have more carbon, more nitrogen, more oxygen than one forming in a metal-poor environment, and the specific conditions, temperature, pressure, radiation environment, dust composition in the protoplanetary disk, all affect what molecules form, what ices condense, what chemistry occurs. 3i Atlas carries, frozen within it, a record of those conditions, a snapshot of its birth environment. The delayed appearance of C2, the specific volatile composition inferred from observations, these are clues, hints, whispers from another stellar system, another time, another place. The organic precursors that drive emissions, complex carbon-bearing molecules, formed perhaps in the cold outer regions of the protoplanetary disk, or inherited from the molecular cloud that collapsed to form the star and planets. These organics, often called distributed carbon, represent a significant fraction of cosmic carbon, not in simple molecules like CO or CO2, not in pure graphite or diamond, but in intermediate complexity compounds, chains, rings, functional groups. This organic inventory, poorly understood even in solar system comets, even more mysterious in interstellar visitors, contributes to the red colour when processed, to the green emissions when fresh material sublimates and photodissociates. It is, in a sense, the most interesting component, the bridge between simple inorganic chemistry and the complex organic chemistry that life requires. Drift deeper now into relaxation and consider the fate of the comet after this passage, after receding from our sun, growing cold again, quiet again. It will continue on its hyperbolic trajectory back into interstellar space. Billions of years from now, it may enter another stellar system, encounter another sun, undergo another awakening, another transformation, or it may wander forever, never again feeling stellar warmth, carrying its remaining volatiles sealed beneath the processed crust, a time capsule, a memory, until perhaps, unimaginably far in the future, it collides with something, a star, a planet, another wanderer, or simply dissipates, eroded atom by the thin interstellar medium. Eventually, like all things, it will end. transform into something else. But that ending lies so far ahead, so many eons distant, that it seems almost like no ending at all, just continuation, persistence, eternal drift, the lessons for future interstellar visitors, and there will be more, certainly more, inform how we plan observations, what instruments we prepare, what questions we prioritize. We've learned that early observations should use red filters, document the dust phase, while later observations need green and blue filters, spectroscopy, to catch the gas emissions. We've learned to expect layered activation, surface depletion giving way to interior richness. We've learned that color is diagnostic, meaningful, carrying information about composition and chemistry. Each interstellar comet teaches us, prepares us for the next, builds our understanding incrementally, and perhaps, decades from now, we'll detect an interstellar comet early enough, far enough out, to send a spacecraft, to intercept, to sample directly, to touch and measure and analyze, to answer questions that remote observation cannot. The dynamic activation process, this transformation from dormancy to activity to dormancy again, mirrors cycles we see throughout the universe. Stars ignite, burn, fade, galaxies form, evolve, merge, planets differentiate, geologize, cool. Nothing is truly static. All is transformation. All is change occurring at different timescales. The comet's color change, compressed into months, is unusually fast, visible to human observation, but the principle is universal. Heat brings change, brings revelation. Distance brings quiescence, brings sealing. The universe breathes, cycle, transforms, and we observing are part of that process, consciousness arising from cosmic chemistry. Observing cosmic chemistry, a strange loop, a beautiful closure. The interstellar hue drift we've discussed, this journey from red to green and eventually back toward dormancy, represents a specific trajectory through color space, wavelength space. If we could graph it, plot color versus time, we'd see a curve starting red in July, shifting orange, yellow, green, peaking in green around November-December, then fading. We could parameterize this curve, fit it with equations, predict future behavior. This is what astronomers do: quantify the qualitative, measure the beautiful, not to diminish beauty, but to understand it more deeply, to see patterns, to find universal principles. Color becomes data. Data becomes understanding. Understanding becomes appreciation. Feel your body now completely relaxed, heavy, sinking into softness, and imagine the eternal color stillness that awaits the comet when it's far enough from all stars, in the deep interstellar void. No light illuminates it, no colors exist, only darkness and cold, temperature approaching, but never quite reaching, absolute zero. In that stillness, that silence, time loses meaning. 1 billion years passes, feels like nothing, no sensation, no change, no markers, just existence, pure, simple, without observation, without light. Does color exist? The comet possesses the potential for color, the materials that would reflect or emit specific wavelengths if illuminated, but in darkness. The potential remains unrealized, latent, waiting. This is the comet's natural state, its default. and the brief months of colour we observed are the anomaly, the exception, the rare moment of revelation in an eternity of darkness. The reddish dust, those first observations, represented the exterior, the weathered surface, the memory of what the interstellar medium does to expose material. Over time, with patience, the green gas, the later emissions, represented the interior, the preserved pristine material, the original composition less affected by processing. In this way, the colour change was a journey from outside to inside, from age to young, from processed to preserved. We watched, in real time, as the comet peeled itself, revealed itself, layer by layer. The red was honest, showing its age, its journey. The green was honest too, showing its youth, its origin, both true, both meaningful, telling different parts of the story. Think of the comparison to Earth's own transformations, seasons, day and night, ice ages and warm periods. Our planet too cycles through states, changes colour when observed from space, white in ice ages, blue-green normally, redder perhaps in past epochs with different atmospheric chemistry. We understand these changes, live within them, but observing a comet's transformation, compressed in time, visible in months, gives us perspective, lets us see change itself as a fundamental property, not of comets specifically, but of systems in general. Everything changes, given energy, given time, given the right conditions. Stability is temporary, equilibrium is local, change is universal. The protective layer the comet built up, or had built upon it, during interstellar transit, served its purpose. It prevented the interior from sublimating away, from being lost atom by atom to the vacuum and radiation of space. Without that protective crust, the comet might have arrived completely devolatilized, just a rocky core, no volatiles remaining, no potential for colour change. The red Tholin surface, though it initially hid the green interior, ultimately preserved it, made the later revelation possible. This is a kind of cosmic irony. The same processing that depletes and darkens the surface also protects what lies beneath, seals it, saves it for eventual release. Let the rhythm of your breathing guide you deeper, each exhale releasing, each inhale receiving. Imagine breathing out red, dust, surface concerns. Breathe in green, fluorescence, deeper peace. The diatomic carbon molecules, those C2 pairs, become your breath, simple, essential, glowing when energized, resting when calm. You are the transformation, the color change, the journey from red to green, from complexity to simplicity, from tension to release. The swan bands, those specific wavelength ranges where C2 emits, are named for William Swan, a 19th century Scottish physicist who first studied these spectral features. He observed them in carbon-rich flames in laboratory conditions over 150 years ago, never imagining they'd be used to study objects from other stellar systems. His careful work, his patient spectroscopy, laid groundwork for discoveries across space and time. This is how science builds, each generation contributing, each observation adding to the foundation. Swan could not have conceived of interstellar comets, of Gemini North telescopes, of digital imaging, but his work enabled all of it. This continuity, this accumulation, this building of understanding across generations is humanity's long project, our slow transformation from ignorance to knowledge, from blindness to vision. The CN violet system, emitting at shorter wavelengths, adds blue tones to the overall appearance. Cyanide, toxic to life as we know it, but beautiful in emission, contributing to the blue-green palette. The specific shade of green an observer sees depends on the ratio of C2 to CN. More C2 gives yellower green, more CN gives bluer green, and both depend on the parent molecules, the organics in the ice, and the UV flues and the photodissociation rates, everything connected, everything affecting everything else. The coma is a system, an ecosystem without life, where components interact, balance, create emergent properties like color that arise from the combination, not from any single process alone. Feeling so peaceful now, so quiet. Let your thoughts become like the far tail of the comet, distant, dispersed, fading, the red dust persisting in that tail, drifting, spreading, becoming ever more tenuous, eventually indistinguishable from the interplanetary dust that fills our solar system. Every comet adds to this dust, contributes particles, and over millions of years, the accumulated dust from all comets creates the zodiacal light, that faint glow visible from dark sites, stretching along the ecliptic. We see it. We swim through it as Earth orbits. We are part of it. And 3i Atlas adds its contribution, a few tons of dust, a tiny fraction, but real is material from another stellar system now mixing with ours. Interstellar exchange, cosmic commerce. The observations continue, will continue, as long as the comet remains detectable. Each night it fades a little more, recedes a little farther, eventually, in 2026 perhaps, or early 2027, it will be gone, too faint even for the largest telescopes. The observations will stop, not because interest wanes, but because there's nothing left to see. The comet will still exist, still be there, but invisible, too far, too dim, and it will continue, silently, invisibly, back into the dark, carrying what we learned and what we'll never know, sealed within it, until perhaps another encounter, another sun, another awakening in another era of the galaxy. We are drifting now, deep into phase 3, into the gentle fade. Let the concepts wash over you, abstract, peaceful, no longer specific facts but feelings, sensations, veiled red awakening. Can you feel it? That initial state, hidden, potential, emerald gas emergence, rising, revealing, quiet color surrender, letting go, releasing, dust to glow shift, transformation, natural, inevitable, hidden fluorescence peace, waiting within, molecular green whisper, soft, gentle, barely there, Tholen veil dissolution, fading, disappearing, revealing light beneath, diatomic calm radiance, simple, pure, two becoming one, layered hue serenity, levels of color, levels of consciousness, organic red fade, the exterior releasing, celestial jade breath, inhale green, exhale peace, buried carbon bloom, deep within, emerging slowly, solar-induced verdant hush, warmth bringing quiet transformation, coma palette evolution, changing, flowing, one color to another, pristine glow integration, everything combining, everything whole, red dust memory, remembering where you've been, green emission harmony, arriving where you're going, chemical depth reveal, layers opening, showing what was hidden, interstellar hue drift, wandering through color space, through consciousness, eternal color stillness, approaching, nearing, the final quiet. Breathe, just breathe. Veiled red awakening in the distance, emerald gas emergence rising, quiet color surrender washing over, dust to glow shift completing, hidden fluorescence peace settling in, molecular green whisper fading, tholin veil dissolution almost complete, diatomic calm radiance all around, layered hue serenity, organic red fade, celestial jade breath, buried carbon bloom, solar-induced verdant hush, coma palette evolution, pristine glow integration, red dust memory, green emission harmony, chemical depth reveal, interstellar hue drift, eternal color stillness, so close now, so near. Everything quiet, everything still, veiled red, emerald, quiet, dust, glow, hidden, molecular, tholin, diatomic, layered, organic, celestial, buried, solar, coma, pristine, red, green, chemical, interstellar, eternal, color, stillness, peace, transformation, complete, returning, beginning, ready to drift, far, far out, again and again to explore. This is your weekly dose of 3i Atlas featuring 3i Atlas.